Okay, good morning to one and all. I welcome you for the session of heat transfer lab. Today we shall discuss an experiment on unsteady state of heat transfer. We also call it as transient state of heat transfer. Maybe in our theory class we have learned about this phenomenon of heat transfer called as unsteady state heat transfer. If you remember, unsteady state means it is the condition of a body where its properties keeps on changing with respect to the time. When we say steady state heat transfer, the energy transfers in such a way that the properties of the fluid or any given body which is under consideration doesn't change with respect to time. Okay, so here in this experiment we will study about unsteady state of heat transfer, where we are going to consider a body whose temperature will keep on changing as the time progresses. Okay, so that typical phenomenon we are going to discuss in this mode of heat transfer. Okay, so in this apparatus we will basically come across a specimen where we will make it to undergo heating as well as we will make it to undergo cooling. But during this phenomenon, heating and cooling, will come to know how the temperature of a given specimen keeps on varying with respect to the time. That is what is the main aim of the experiment. Okay. So to give one or two examples about the unsteady state heat transfer where we come across in practical situations, let me give an example of a heat treatment process like quenching, annealing, right? In all of these processes, what we do is the ingot or the material whose properties needs to be changed, right? We will heat that material to a crystalline temperature, then we suddenly dip it into a fluid medium whose temperature is very less. Take for example, in quenching, we will heat the material to a very large temperature, then suddenly we will place it onto the water or any given medium, or you can say also sometimes we will expose the body into the air. So thereby, because of the temperature difference between the body and the ambient, be it oil, be it water, or be it any air, right? The heat transfer occurs by convection. Okay, so where the body temperature will keep on changing, whether it is going to increase or decrease with respect to time. If it is a case of heating, the temperature of the body will keep on increasing with respect to the time. If it is a case of cooling, then the temperature of the body will keep on decreasing with respect to the time. So these are the two cases we basically come across when we study the phenomenon of unsteady heat transfer. So here also in this apparatus, today we are going to have a specimen. You can see this cylindrical specimen, right? So where it has got some diameter and the length. So this is our main attention. So we are going to study the unsteady heat transfer in this particular specimen. For that, what we do, we will study basically here two different cases. One is the heating of this specimen, second one is the cooling of this specimen. So our main aim of the experiment today is to understand and measure the temperature variation with respect to time for this specimen. So as I already told you, we will first conduct the experiment for the first case called as heating. So our aim is to first start heating this specimen in such a way that its temperature will keep on increasing as the time progresses. So in order to do that, what we have done is, in this apparatus we have a oil chamber. We have an oil chamber in which we are going to use typical oil, say 20 or 40 oil. We are going to fill it into this chamber to the desired level. Then we are going to heat the oil first. We are going to heat the oil to a desired temperature. So that becomes our hot oil in comparison with this specimen. Okay, so as I already told you, the main aim in the first half of the experiment is to heat this specimen. So in order to heat the specimen, we are going to have a hot oil. So as I mentioned, the oil is placed inside this chamber. Then we are going to use this dimmer stand so that we can give the electricity to this oil for the heating. So we will wait for some time such that the oil will be increased with temperature to a desired level. Let us say the temperature of the oil. Here we are going to measure it as T1. So you can see in this details, the first one, it represents the temperature of the oil bath. So oil is placed here initially. So we'll keep on giving the power supply such that with the help of a heating coil, we start heating the oil to a desired temperature. Let us say we are heating the oil say up to some 95 degrees Celsius. So till then we keep on heating it, then we'll switch off the power. So now we are having a readily available hot oil with a temperature T1 representing say 95 degrees Celsius. So that becomes our the first state, where now once the oil is at higher temperature, now what we do is we will now take the specimen. So this is, as I already mentioned, this is our specimen for which we are studying the unsteady heat transfer. So this specimen, now we need to heat it. So we already have a readily available hot oil. So what I do is I'll just dip this immediately into this oil chamber. Imagine there is a hot oil inside this, having a temperature 95 degrees Celsius. So before I insert this specimen, we will measure the specimen temperature, initial temperature. Let us say it is T2. You can see in this catalog it is T2. So T1 stands for oil temperature, okay, which will be high temperature, say 95 degrees Celsius, and T2 stands for the specimen temperature. So as I told, the specimen, this is the specimen. It is in the cylindrical shape, having some length and diameter. So before I dip it into the oil, what is the initial temperature? Before I start with the experiment, say at the time t equal to 0 seconds, what is the temperature of this specimen? That we will measure initially as T2. Okay. Then once we measure it, then we shall place it onto the hot oil bath like this. So now you imagine there is a oil which is very hot and there is a specimen which is comparatively colder. So when both of them are brought in contact directly, so what happens is, because of their temperature difference, the energy transfer in the form of heat occurs. You will note here that the specimen will start now absorbing the heat from the hot oil, thereby its temperature starts increasing slowly. So as we say, during this experiment, since it is an unsteady heat transfer or a transient heat transfer by convection occurs in this case of heating, what we do is we will take down for every 20 seconds. We will have a stopwatch. So using that, for every 20 seconds, we keep on noting down the values of T1 and T2. You can very easily understand here, since there is a hot oil and there is a specimen, because of their temperature gradient, the heating of the specimen keeps on happening. So because of this, we will note that T2 will slowly increase. T2 will slowly increase, which is a specimen temperature. On the other way, since the oil is losing the heat, it will start reducing with the temperature. So as the time progresses, say for every 20 seconds, we are going to note down the reading for T1 and T2. So this process will keep continuing until we will come to a stage where you will come to know that T1 and T2 becomes equal. So I mean to say, T1 is the oil temperature, since it keeps on losing the energy, and T2 is a specimen temperature which keeps on grabbing the energy. So at one point of time, say after some few minutes, you will see that temperatures T1 and T2 becomes almost equal. So until that, we should keep on taking the readings for every 20 seconds about T1 and T2. So once we come to know that T1 becomes almost equal to T2, we will understand that now the heat transfer ceases between the specimen and the oil. Because whenever there are two bodies which are at same temperature, then after that you cannot have the heat transfer process by any mode of heat transfer. So that concludes our experimentation part about heating. So that is a point where we are going to stop the experiment for heating of the specimen. So now at the end of the experiment, you will see that the T1 and T2 becomes equal, and this specimen will now become a very hot specimen at higher temperature. And during these readings, what we understood is that specimen temperature has continuously increased with respect to the time. So that's why we are considering it as an unsteady heat transfer. So temperature is varying with respect to time. So it is an unsteady state of condition for the body. Okay, so that's the first part of the experiment, which is about heating. Now, once we take down the readings of temperature of specimen, temperature of oil, as well as the time taken for every 20 seconds, we will make a tabulation of all these three parameters. Then based on these readings, we shall plot a graph. Okay, we shall plot a graph of temperature of the specimen on y-axis and time taken on x-axis. Okay, so once you plot with all these readings, we can get a locus of all the points, which we get it as a heating curve. So because the heating of the specimen is occurred, the graph what we arrive at is called as the heating curve. So which I am going to show you after a couple of minutes. Okay, so that is a heating curve we can arrive at. So that graph needs to be plotted down after the tabulation. Okay, so that is the first part of the experiment. Now we are having the hot body, which is our specimen. Now what we do, the next half of the experiment, now we shall cool down this specimen. So in order to have that, again we are having a chamber. Okay, there is a air chamber provided here in the next half of the apparatus, where you can see inside this there is a blower or a fan being placed. So we are going to use, we are going to switch on this fan such that it will force the air to flow into this chamber. So air will now with some velocity it will flow into this chamber and it will get exhausted on the other side. Okay, so now initially the air is at some atmospheric temperature. Let us say it is around 27 to 28 degrees Celsius. Now what I do, since we are already done with the first half of the experiment, the specimen is very hot now. So this acts as a hot body in comparison with the air which is entering into the chamber. So there exists a temperature gradient between the specimen and the air. So now what I do, now similarly in the same set, what I do is I just place this into the air chamber. You can see now there is a hot body which is now directly exposed to the flowing air. So as I mentioned, the hot body, the specimen is hot in comparison with the air flowing into the chamber. So definitely again convection occurs. Convection mode of heat transfer occurs. Thereby the specimen starts cooling down. So before we do this experimentation, again we are going to note down one more temperature, which is the temperature of the air. We call it as T3. So there is a thermocouple being placed in the chamber which will measure us what is the temperature of the air. So before the start of the second part of the experiment, we shall first measure what is the initial, when the time taken is t equal to 0, we shall measure the temperature of the air. Then we shall insert the specimen, which is a hot body, into the flowing air. So then convection occurs, slowly the air starts grabbing the energy from the specimen and it starts cooling down. Okay, so as usual again, for here we can note down again the temperature in the second half. Please note that we are going to note down the temperatures of T2 and T3. But in the first half of the experiment, we had noted down the temperatures for T1 and T2. Because the first half was heating of the specimen and now the second half is about the cooling of the specimen. So cooling is happening for the air, for the specimen in respect to the air. So we shall note down now T2 and T3 accordingly. So for first half T1 and T2, and for the second half of the experiment we shall note down T2 and T3. So since T2 is a specimen temperature which keeps on reducing as the time progresses. So again, for say every 20 seconds, or sometimes we shall also note down for every 10 seconds, what is the temperature of the specimen, T2. And on the other way, since the air is getting warmed up because of the energy lost by the specimen, we shall also note down the temperature of the air. So T2 and T3 will be noted down. So this we shall continue in such a way that again one point of time you will come to know that T2 and T3 may become equal. Like we have seen in the heating of the specimen, the T1 and T2 became equal. Here also T2 and T3 also become equal. After some time, say some few minutes, you will see that T2 and T3 become equal. So that is a point where we are again going to stop the experiment. So that will conclude the cooling phenomenon for the specimen. Now, having noted about the temperatures of air and the specimen with respect to the time, again we are going to draw one more plot or a graph of temperature of the specimen now with respect to the time taken. So in the previous case we had drawn the heating curve. Now this will give us the cooling curve. So the cooling of the specimen. So heating and cooling for the specimen is going to be well understood by conducting this experiment. So this is how we carry out the experiment. So only temperature readings we are going to note down. So T1, T2 and T3 are most important in arriving at the cooling and heating curves. Okay. So here the thing to be noted is the specimen material and the specimen dimensions will be known to us. Using that and using the material properties, we can proceed further to calculate at any given temperature, at any given point of time, what is the temperature of the specimen, be it in cooling or be it in heating. If at all, if you want to calculate theoretically, we are going to have a series of formulae. Using them, we can very easily calculate. Okay, so since the natural convection is happening in case of heating and forced convection is supposed to happen in cooling, so we shall use the calculations of same what we have done in our previous labs for natural and forced convection. Similar kind of formula we are going to use to calculate what is the heat transfer coefficient H. Okay, so once H value is calculated using the transient phenomenon, using a typical mode of analysis called as lump system of analysis, we shall calculate the temperature of the specimen at any given interval of time. So I am going to show you a set of calculation related to this, and I will also show you the graph how we will get to know for cooling and heating of the specimen. Okay, you can have a visualization about the apparatus once again. So the reading what we take here is only temperatures, but the experiment is conducted in two stages. One is for heating the specimen and another one is for cooling the specimen. Okay, for heating we use the hot oil, and for cooling we use the atmospheric air for cooling. That's what we are going to do with the experimentation. Okay, now coming to the calculation part of it. So as we have seen from the experimentation, we are going to note down the tabulation like this. So I repeat again, so we are basically noting down two temperatures for each of the case. So if I discuss about the heating of the specimen, so we shall make a tabulation of the oil temperature, which was our T1, and we shall note down the temperature for specimen, which is our T2. So T1 and T2 are noted down continuously for a given time interval. Say time interval is represented as T. So what we do is, for every 20 seconds, say we will start our experiment with 0 seconds at the start of the experiment, we shall note down initially. So initially the hot oil is at, let us say, is at 94 degrees Celsius. Then the specimen temperature, which is our atmospheric temperature of the specimen, before inserting into the oil, it is, say it is 34.7 degrees Celsius. Okay, it is at the start of the experiment. So I have written here 0 seconds. Now, as the time progresses, when the specimen is placed into the oil bath, you will see that the temperature of the specimen keeps on increasing. Okay, here I have just listed out only 3 readings, in between intermediate readings I have written, but it's a big tabular column involving n number of readings. So for every 20 seconds, what I am trying to tell is 0 seconds, 20 seconds, 40 seconds, 60, 80, 100 seconds. So like this, for every 20 seconds, you should note down the values of T1 and T2. That is what has to be done. Okay, so because we do like this, you can see from the readings that the temperature of the oil, you can see here 94, 86, 82, the temperature of the oil is keep on decreasing because it is giving out the heat. On the other way, the specimen, since it is inserted into the hot oil, its temperature will now keep on increasing. You can see from these 3 readings, the temperature of oil is decreasing, temperature of the specimen is increasing. That indicates the specimen is getting heated up. So that's why we are calling it as heating phenomenon. Okay, so I told you during the explanation that at one point of time, okay, we will see that the temperature of the oil and the temperature of the specimen become equal. So that is a point where we are not going to further take the readings. We will stop the readings, stop taking the readings at that point of time. So you can see in this tabulation for 620 seconds after the start of the experiment, we have seen that T1 become equal to T2. So 82.4, 82.4. So we shall stop with the experimentation. So having noted with this table for heating, we can now see that, as I told, we are going to plot a graph of temperature of the specimen T2 versus the time interval in terms of seconds. Okay, so with those readings, you can draw the graph. So once you draw the points, you can take the locus of that points and you can get a curve like this. So since that is a heating phenomenon, you will see that as the time increases, you will see that the specimen temperature keeps on increasing like this. Okay, so this curve we call it as a heating curve. So this is what we are going to plot by taking down that tabulation. Okay, so once we are done with this, now we need to calculate. The main part of the experimentation is about understanding how to calculate theoretically the temperature of the specimen at any given time interval. For that, we have a series of calculations. I have just listed out a few points here. So I was mentioning that it is a convection happening, natural convection that happens during the heating phenomenon. So in your regular lab, you have studied already about the natural convection phenomenon. You have conducted an experiment where you could calculate the value of H. Okay? In the same manner, you are also going to calculate H here because natural convection is happening. So to begin with, what we do is, since I am considering only heating phenomenon now, so we shall note down the maximum and minimum temperatures in this experimentation. So initially, our oil was at highest temperatures, 94 degrees Celsius. So this is our Tmax. So this is our Tmax. And our specimen was at a minimum temperature, which is at atmospheric temperature. So this is Tmax and this is Tmin. So later on, they will keep on changing. So these are the temperatures we are going to note down, and based on that we shall calculate the average temperature of the the air or oil. Okay. So once we calculate mean temperature, so using this mean temperature, we shall refer the table, property tables for the given oil. So the oil which we consider here is SAE 20. Okay. So using the data handbook for this oil, for this mean temperature, we'll note down the different properties. Okay. So by using those properties, we basically, as we have seen in the natural convection, we first calculate Grashof number. The standard formula is known to you. So using that, Grashof number is calculated. And once the Grashof number is calculated, then Prandtl number is noted from the data handbook. So using these two values, we will calculate Rayleigh's number. So once the Rayleigh's number is obtained, so looking at the value of the Rayleigh's number, we have a series of correlations given for Nusselt number. We select accordingly and we shall calculate finally Nusselt number. And once the Nusselt number is obtained, by definition, Nusselt number is given by definition, Nusselt number is given by HL by K or HD by K. Okay. So here, using that Nusselt number definition, we will finally calculate what is the heat transfer coefficient between the specimen and the hot oil. So that we are going to get it by using this series of calculations. So I have not written here formula because I hope that you already know the formulas, and anyhow they are available in the manual which is provided. Okay. So once H is calculated, then later we shall continue further by calculating a new term called as Biot number. So knowing the value of H, which is just determined, so knowing the diameter of the specimen and knowing the thermal conductivity, we use this formula for Biot number and we shall calculate the Biot number. Okay. So once Biot number is calculated, depending on its value, what we get. So let's suppose if the value of Biot number obtained, if it is less than 0.01, okay, it has to come less than 0.01. So based on this value, we are going to use lump system analysis for the transient heat transfer. So in that, we have a standard relation for temperature distribution. Okay, where this is T, you can see this, I will read out the formula, T minus T infinity divided by T naught minus T infinity, okay, is equal to E raised to minus Biot number into Fourier number. So this is a standard formula we use for lump system analysis, where here the T represents the temperature of the specimen and T infinity represents the temperature of the ambient. So here the ambient for heating is the oil. So we need to note down the value of T1 here. And this T we are supposed to calculate. And what is this T naught? It is the T naught is the initial temperature of the specimen at the start of the experiment. Okay, when time was 0 seconds, what is the temperature? T2, 34.7. That you need to take it here. Okay, so that should be equal to E raised to Biot number into Fourier number. So Biot number is already calculated and Fourier number is given by alpha T divided by Ls square, where alpha is called as thermal diffusivity. You get it from the data handbook. And T stands for time taken. So you are calculating time temperature, say for any given time. Okay, so that time you have to substitute here. And what is this Ls square? Ls stands for characteristic length of the given specimen. So which is given by this formula, pi r square L divided by 2 pi r into r plus L. It is for cylinder. Okay, basically the specimen is in cylindrical shape. We use this formula for calculating characteristic length. So once we do that, we shall calculate Fourier number. So that value you substitute here and get the value of temperature of the specimen canonical. So like this, using the same formula for any given time interval, you can keep on using this formula and you can get the value of temperature accordingly. So that is our theoretical temperature of the specimen. And already you have written down the experimental values of specimen during our experimentation part. So once you get the theoretical values and the experimental values, you can have a comparison between them and you can accordingly conclude the experiment for heating. Okay, so this is all about heating part. The same way you can proceed further for the next half of the experiment, that is about cooling of the specimen. So here for a change what happens is during cooling the specimen is hot and the ambient becomes our air, which you have seen in the apparatus there. So the specimen is inserted into the air so that specimen keeps on cooling. So again we shall make a tabulation for a specimen temperature as well as the air temperature. The specimen temperature was indicated as T2, so we will note down the temperatures like this, which will keep on decreasing because it is getting cold. And the other way, temperature of the air, though since it is a huge volume of air entering the chamber, you may not see drastic variation in the temperature, but you will see the variation anyhow. Okay, so temperature obviously it has to increase. You can see in this way. Okay, in this it is decreasing. Okay, but that doesn't matter for us. We are only concerned about the cooling of the air, the cooling of the specimen. Okay, so you can see here we will come across a situation where again the temperature of the specimen and the temperature of the air becomes equal. So until that, for every 20 seconds or 10 seconds, again you note down the things. Okay, and you can do up to this point where you can stop your experimentation. So tabulation can be done like this. Again, based on this tabulation, again in the same graph what you used earlier, okay, you can again now draw the graph of temperature of the specimen T2 versus the time taken using this tabulation. You will see that the nature of the graph will be like this. You can see that as the cooling occurs, the temperature of the specimen keeps on decreasing like this, until the temperature of the specimen becomes equal to temperature of the air. So this curve we call it as cooling curve. So since the specimen is initially made to undergo heating, we are going to draw the heating curve, and later on we are going to make it undergo cooling, so we can draw the cooling curve. So this will give us the understanding of cooling and heating of the given body during transient heat transfer. So again the same kind of calculations, okay, is going to be carried out. We will finally calculate the value of H. Then based on the value of H, Biot number is calculated. So looking at the value of Biot number, we shall use the lump system analysis, for which the same formula for temperature distribution is taken down, and again temperature for given time can be calculated very easily. So those temperatures calculated for cooling can be compared with the temperatures that we have got experimentally for the specimen. So we can compare the results of theoretical and experimental values of temperatures, and accordingly we can conclude with our experimentation on the transient heat transfer. Thank you.